Okay. So, the two basic parameters for a random variable, we have this parameter which is the expectation mu, this other parameter which is the standard deviation sigma. And there's very clear qualitative interpretations to both mu and sigma. So mu can be an arbitrary real number, and it tells us what to expect for the long-term average of this random variable, which is some numerical quantity we're measuring over and over again. And usually, when people are interpreting statistics, the random variable has a sign convention, and the purpose of the experiment is either to determine the expectation for purposes of intellectual inquiry, or to maximize the expectation for some sort of practical purpose. And, the determining the expectation for purposes of intellectual inquiry obviously kind of has an epistemological priority above making decisions based on whether this thing is positive or negative. But usually the way expectations are used to make decisions is that if the expectation is positive, then you should do whatever it is that gives you this positive expectation as often as possible because you think that it's good. And if you want to ask more numerical questions, it's more or less universally reasonable to center the expectation at 0. So the real process of statistics has to do with the extent to which data shapes around its expectation. And from that point of view, there's no real mathematical insight obtained by keeping a non-zero expectation. So it's very common to center expectations at 0, and in that context, what the standard deviation tells you is just the typical size of what you sample as a positive or negative deviation from 0. If your expectation is not 0, the standard deviation tells you the extent to which your data is concentrated around this expectation as opposed to being widely spread out over a range with lots of overestimates canceling out lots of underestimates. So mu is an arbitrary real number, and usually it's interpreted with the fundamental sign convention that positive expectation is good. You want to maximize expectation. And with sigma, sigma is like some kind of positive parameter, and a low value of sigma tells you that the expectation is an extremely good model for the data, in the sense that the data looks like small variations on the expectation in pretty much every cell. And a large sigma tells you that there's like half the cells which substantially underestimate mu, and half the cells which substantially overestimate mu. And we had the de Moivre-Laplace theorem as a way of getting more information about probabilities related to mu and sigma. And later on, for independent, identically distributed random variables, we'll have this central limit theorem, which tells you basically the same thing as the de Moivre-Laplace theorem, but in a more general context. And so there's another way you can get information about probabilities related to mu and sigma, which is much more finitary and quantitative. I'm going to introduce that now. Okay, so the most general answer you can get about the extent to which random variables concentrate around their mean is this thing called Chebychev's inequality, which I've highlighted in teal. So there's a lot of information in the teal equation, but it has a very clear interpretation. It's like you're asking for the probability that what's called an empirical average falls within an error interval around the mathematical expectation. So, you have some sort of process which you think you have a probability mass function or a probability density function, and using that you calculated mu. And then this inequality is telling you that a certain lower bound holds on the probability of an average of samples being within mu minus c sigma n and mu plus c sigma n. So the thing in the middle of the probability with x1 plus xn over n, that is supposed to represent what you actually measure from this random process you believe you've modeled with these variables. And you're looking at the average of what you measure in the first n samples. And the simplest idea in probability is that this average you measure empirically should be close to mu. And, well, you want to understand the extent to which that's actually true. You need to measure your errors in terms of standard deviation. And so we have an average that's being measured with an error interval around the mean, and the error interval is in units of standard deviation, and this parameter c is telling us the width of the error interval. And the right side of the inequality should be thought of primarily in the context where c is fixed and n is going to infinity, or at least in the context where c squared is not small enough to cancel out the n squared, and the subtracted term approaches zero, giving a probability approaching certainty. So if c is fixed and n is going to infinity, this gives you a probability approaching certainty that an empirical average is within an error interval around the mathematical expectation. And, this is the scientist's dream. You get a prediction with probability that just spills more nines as you test it over and over again. So the prediction is good if n is larger. You just go from 90% to 99% to 99.9999% and 99.9999999%. But, one message I'll really try to make later on in the lecture is that there is no finite list of nines which actually equals 1. There's a famous thing where human beings are reluctant to believe that the infinite decimal 0.999999 repeating is equal to 1. And, I don't like how that fact is presented in popular culture because it's designed to make people who are reluctant to believe that fact feel stupid. But it's really good not to believe things unless you're sure you understand them. And when people say they don't believe that, what they're reacting to is the fact that they're being expected to understand the concept of an infinite decimal with never having seen any kind of rigorous introduction to it, such that you're telling them that 0.99999, and then you say a word called repeating, and you say this is 1, and they're like, what? What does this word repeating have to do with 0.999 being equal to 1? People correctly intuit that no finite list of nines equals 1, and they correctly intuit that nobody's ever rigorously constructed the word repeating in the context of numbers. But, the point about Chebychev's inequality is that it's not an abstraction that requires an infinitary limit. There's no infinities in this Thiel statement. It just tells you that a certain number you can either calculate or use infinitesimal calculus to define. This number is bigger than another number. And that means you can get information from this inequality no matter how ridiculously extreme the parameters are. That's the issue with the infinitary limits in the central limit theorem or de Moivre-Laplace's theorem. It's that the approximations in those theorems hold for a certain range of parameters, and if the parameters are excessively extreme and you try to get tremendous sequences of nines out of the central limit theorem, you're going to stress the mathematics where it doesn't want to go, and you'll ask for infinitary limits to converge faster than they do. And so Chebychev's inequality, on the other hand, just produces as many nines as you can calculate without any necessity to be delicate about infinitary limits. If you can make this n really large, and you're in a situation where sigma n is not too much larger than n, you can, sigma n should be something like square root of n, or at least smaller than n, and then the probability on the right side of this thing just starts converging to 1. And as n gets larger, you just get a stronger and stronger certainty that the average of what you see will fall within a certain error interval around the mean. And, this is a inequality, which means you often want to translate it into infinitary statements by choosing specific values of the constant c as n gets larger. So you can have some flexibility in how you use this by scaling the constant c so that it balances the width of your error interval with the rate of convergence to certainty. So c is something you can adjust in application of Chebychev's inequality. Large value of c gives you a wide error tolerance and a fast rate of convergence to certainty. A smaller value of c gives you a smaller error tolerance and a slower rate of convergence to certainty. But the basic idea you always want to keep in mind is that if sigma n is being balanced out by this thing c, and c is getting small at a rate that keeps c times sigma n controlled, then this power or this quantity will be very close to 1, because what happens if this theorem is useful, and the case that's always hoped for in probability is that the standard deviation scales like the square root of the sum, or which is what happens when the random variables are independent, or that the standard deviation at least scales sublinearly. And if c is scaling sublinearly, or if sigma n is scaling sublinearly, then you can adjust c so as to get a sublinear growth in c, and then subquadratic growth in c squared, or subquadratic decay in c squared, which gives you a non-trivial convergence to certainty. So what I'm describing sounds kind of delicate, because you would like to just use this inequality by fixing C and letting n go to infinity. But that doesn't really work so well because you don't want sigma n to get too big. So usually what you do when you use this inequality is you check how fast sigma n is growing, and then you choose C to cancel it out, which gives you a fixed error interval. Okay. So we can use this Chebychev's inequality to come to some interesting conclusions that have very clean formulations in natural language about what's possible or impossible for probabilistic games. So we've been implicitly using the word game to refer to an experiment together with a sign convention. So experiment, you just kind of observe something. You play a game, you observe something with an intention to maximize it. So we've been thinking about these games that can be interpreted mathematically as uncorrelated, identically distributed trials of a random variable. And the word fair means the random variable has zero expectation. So the concept of fairness is tied to zero expectation through the idea that anyone with mathematical computation ability and access to the model of the random variable can determine the expectation. And if you want to conduct further analysis, it's best to recenter things at zero so you're playing a fair game, because otherwise things just get overwhelmed by the fact that one side is making a consistent rate of return. So once you have a fair game, then you get this nice interpretation where the random average is just expected to be very small, and what's implied by Chebychev's inequality is approximate certainty of the average being really small. And so we calculated previously that for independent, identically distributed random variables, the standard deviation of the sum, which we're calling sigma n, is equal to the square root of n times sigma, where sigma is the standard deviation of an individual trial. So this is kind of why probability theory works. It's because standard deviation scales slower than linearly. Scales like square root of the original standard deviation. And so we have this interpretation of the phrase any fair game, which is just an uncorrelated, identically distributed trials of a random variable with zero expectation. And the standard deviation of a fair game after n trials is the square root of n times the standard deviation after one trial. And so we can interpret the phrase positive rate of return as making an average of R dollars from the game. And usually this is the way people use the phrase rate of return because they're asking for a consistent profit over time. So it's like you think the random variable is some phenomenon that's happening every second or every minute or every hour, and a positive rate of return means you can expect this thing to produce money at a consistent rate over time. And if you don't have a positive rate of return, you can't expect it to produce consistent profit. And so we can see why it's mathematically necessary to underperform any target for your rate of return in a fair game. Because we want to make a clever balancing choice in this constant sigma that appears, or this constant c that appears in Chebychev's inequality. So what we want to choose is the rate divided by the square root of n times the standard deviation. So let's have a look. Why is that a good choice? So we're trying to choose c to be rate divided by sigma n. So we want a rate of return r, and we plug in c equals r divided by sigma n. And then we plug in c equals r divided by sigma n to the right-hand side of the formula. And because sigma n only has a square root n in it, when you square that, it fails to cancel out the denominator and gives you a linear decay to certainty because the denominator still has an n in it. So just to say again, sigma n ends up being square root n sigma. And we choose c to be the rate r divided by square root n sigma. And when you plug that into the right-hand side of the formula, you get 1 divided by the square root of n, or the rate divided by square root of n times sigma. And so that's what I have written on the right-hand side of the teal formula. Or not teal on this page. It's now yellow. And we can see that because you have this n in the denominator, as you play more and more trials of the fair game, you're converging to certainty that you underperform any positive target. Okay, so in this example, we can see a generalization of the example in the previous example. So in the previous example, we were talking about achieving positive rate of return on a fair game. And the generalization of that is outperforming the expected rate of return on an arbitrary game. So it's like the expected rate of return in a fair game is 0, and outperforming it means a positive return. And in a general game, you can have a expected positive rate of return, or you can have an expected negative rate of return if you have some other incentive to play the game. And you can try and apply Chebychev's inequality to say that it's impossible to do better than whatever the expected rate of return is. So we want to interpret the idea of a probabilistic game as a sequence of uncorrelated, identically distributed trials of a random variable, where we have these initial parameters mu and sigma. And so I'll just point out that I've used the word uncorrelated here and not independent. Uncorrelated means that the correlation is zero. This is a consequence of independence, but it does not imply independence. In fact, their concept of uncorrelation and independence for random variables is pretty much the same as the concept of the independence equation for two events versus the independence equation for three or more events. You can have uncorrelation, which is all that's necessary to use Chebychev's inequality, whereas the central limit theorem actually requires independence, and it's not true simply with the hypothesis of uncorrelation. But uncorrelation is great because it tells you that the standard deviation squares like you hope as the square root of n times sigma. And we can perform the same balancing act with the constant in Chebychev's inequality, where we put the rate divided by the long-term standard deviation. And Chebychev's inequality tells us something about deviating from the mean in units of the long-term standard deviation. And so we choose the constant to give us the probability of the average exceeding the mean plus the rate of return. And we get the same mathematical conclusion that because it's only a square root of n, it doesn't cancel out the n squared in Chebychev's inequality, and this thing converges to 1. So we can interpret that as saying we're certain to eventually miss any outperformance target. You can't expect to profit from any gain beyond what's mathematically bound up by calculating the expectation. Just want to go back and have a look at Chebychev's inequality again. So the balancing act that we were performing with the constants in those two examples is sort of what I described at the beginning, where this inequality is useful when you choose the constant c to balance out the standard deviation sigma n, so that you get a fixed width for your error interval. And the central limit theorem really uses independence, and it has this infinitary limit, and both of those things just collapse when you think about trivial cases of random variables. But Chebychev's inequality is much more robust, and it actually does tell you stuff even in trivial cases that have apparently nothing to do with the heuristics of probability. So the most ridiculous slap in the face of probability is to say, here's my experiment. I'm going to flip a coin once, and then I'm going to simply claim that it came up that way again and again for the rest of eternity. I'm not actually going to flip it again, but I'm going to tell you that I keep flipping a coin. I'm just going to keep giving you the same answer. I'm going to flip it once, and if it came up heads that time, I'm just going to say this coin kept coming up heads for never. And if it came up tails the first time, I'm going to say this coin kept coming up tails forever. So mathematically, that's indistinguishable from a legitimate experiment. And so we have to accept that Chebychev's inequality is true, even in such a context. So what does this mean in such a counterintuitive context where you don't have any randomness at all in the long term? You were determined forever at time one. And so in this bizarre rigged game where someone is pretending to flip a coin but actually just repeating the same symbol over and over again, what happens to Chebychev's inequality is that sigma n grows like n. And if you try to get information from Chebychev's inequality about this degenerate situation where you flipped a coin once and gave the same answer for eternity, you need to pick C to be roughly 1 over n. And then the right side gives you nothing because C is roughly 1 over n. And that cancels out. So we get a vacuous assertion, which is true but has no content. It just says the right side doesn't actually converge to certainty because in order to control the tremendous growth in the standard deviation, we need to have C decay really fast, and decays faster than n, so we don't get convergence in the right-hand side. And the way you can interpret that is, well, look, if you're going to flip a coin once and give the same answer for the rest of eternity, there is no way to predict that. There is no reasonable prediction, or there's nothing you can say. You're asking about the result of a single coin flip, and probability is what you do once you accept that you can't predict the result of a single coin flip. Okay, so we can have a look at another example here. So let's say how many rounds of a fair coin are needed to obtain a 99.9% probability that the average return is less than a cent. So you have whatever time interval your process is happening. It's happening every second or every hour or every day, and you're asking to make a cent every day. And because it's a fair game, that is unreasonable. You can't make a cent every day from a fair game. So why is that an unreasonable expectation to make a cent every day from a fair game? Well, you can see we have the same parameter calculations that we've been using for our fair coins. And so we can set, or sorry, let me put a bit more information here. Okay, so this is what we need to do. We have a fair game. So this is the coin flip we were thinking about in the context of de Moivre's theorem. And the standard deviation scales like the square root of n, which is the basic reason probability works. So we set the constant to cancel out the growth in the standard deviation. And we get this expression which tells us the rate of convergence to certainty of the probability we fail to meet our cent a day target. It's a pretty slow rate of convergence because a cent a day is a pretty low target, but still we have this term n which goes to infinity and forces the probability up to 1. And so we can ask a computer what n needs to be to have 1 minus 1 over 0.01 squared n equal to 0.999. That gives us n is roughly 10 million. Well, actually, that equation has a precise solution of 10 million, but, we should soften it up because we're just asking for an estimate. But anyways, you play 10 million rounds of a fair coin. You are 99.9% certain of making less than a cent per day. Well, I guess the saying you're doing this every day is kind of antithetical to the message, because with coin flipping in modern data, you can do it a lot more than once a day. Smartphones operate at least 10 billion times a second. People have computers much more powerful than smartphones, and if you're doing something 10 billion times a second, as soon as you make a cent from it, that kind of accumulates. Okay, so this last example is really designed to get you to think about the extent to which extreme parameter values cause softer results to break down, but Chebychev's inequality is extremely robust and will give you information for arbitrary parameter values. And so what are we asked about? We're asked about the probability that a fair game with variance 1 returns at a 10% rate or less after a million trials. So we're asking how implausible is it to make 10% on coin flips. So we want to do the appropriate balancing for Chebychev's inequality. So we ask about the probability of this being, the average being less than 0.1. And so we know that a fair game with a variance 1 is a generalization of our coin flip, and its standard deviation is the square root of the number of trials. So we have 1 million trials, and the standard deviation is 1,000. So we can look at how this compares with the average and see that what we're asking about is the probability of 100 standard deviation anomaly. And so Chebychev's inequality tells you that the probability of 100 standard deviation anomaly is less than 1 in 10 quadrillion. So you want to make 10% on a fair game for a million trials. You can do that once in every quadrillion million. But you can see the yellow notation there. When we're talking about really, really high probabilities, it's unnatural to write them as strings of nines. You have this kind of complementary scientific notation where what you want to do is write these probabilities as orders of magnitude in terms of the subtraction from 1. So we have this extraordinarily high probability that you miss a 10% rate target on a fair game after a million trials. And a good way to write that in scientific notation is to write this as 1 minus 10 to the power of minus 16. So because this is such an incredibly high probability, what you need to communicate is the order of magnitude in the exponent, which just tells you, how many times can I do this while it still looks like 0. If you do it 10 to the 14 times, it's going to look like 0. You do it 10 to the 18 times, well, it doesn't look like 0 anymore. And the issue with de Moivre-Laplace and the central limit theorem is if you ask for the probability of a 100 standard deviation anomaly from the error function, Wolfram alpha gets confused and tells you this number is 1. So as a theoretical mathematician, I can tell you the error function never actually reaches 1. It's always less than 1 for any finite input. So this number is not 1, it's less than 1. But the difference is apparently unphysical. So, Wolfram alpha is pretty smart. It usually gets things right, but it tells me this is 1, and it's not. So that's not really Wolfram alpha's fault. That's more a fact of overstressing the central limit theorem. You can't talk about 100 standard deviation anomalies in the context of the central limit theorem. It's just too far away from the situation where the various parameters actually cancel out to real information. But Chebychev's inequality is just statement about numbers or statement about a certain integral, and I think it's maybe, if you're actually trying to understand what's the probability of making a 10% rate on a fair game after a million trials, it's like, well, once in 10 quadrillion is a better answer than 0. And the central limit theorem is giving me an answer of 0, and Chebychev's inequality is giving me an answer of 1 in 10 quadrillion. And as a theoretical mathematician, the answer of 0 is straight up false, so why not take the answer of 1 in 10 quadrillion? But, there's also a message about the extent to which making 10% on a fair game after a million trials is extraordinarily improbable.